Hi and welcome to my video on mathematical notation with Python. If you are struggling with reading some of the big math notation, but you understand at least the basics of Python, this video is for you. Sometimes math equations can look a bit intimidating, but the operations they represent are often not that complex. What we will do in this video is covering the most common math notation that you might encounter in a book or article, explain how to read it, and then do a simple example implementation of it in Python. By implementing the logic in Python, you will develop an intuitive understanding of what the operator actually stands for. The video doesn't really assume anything more than knowing the basic math operations of addition, subtraction, multiplication, and division. It should also be highly beneficial if you have at least a bit of knowledge on the Python programming language. However, if you don't know how to program in Python, this video might still be advantageous to you, since Python is very easy to read, especially if you compare it to some of the math notation out there. Obviously, I don't pull the knowledge for this video out of a hat, so the content of this video is mostly based on the book Mathematical Notation by Scheinerman. I'll put a link to the book into the description of this video. So the first kind of notation we will cover is about collections. And collections are what they say they are. A collection of a bunch, maybe an infinite amount of numbers. Collection should also ring a bell when it comes to Python. Remember that we also have collections in Python, like lists and sets. So what is a set? It's exactly the same thing in math as it is in Python. It's an unordered collection of unique numbers surrounded by curly braces, like so. 1, 2, and 3. Notice that this is the same thing as writing, for example, 3, 1, and 2, or writing 1, 1, 3, 3, and let's say 2. Remember that sets are unordered. Hence the first and second set is the same. It's the same numbers in different order. Still the same set. Also, sets are about unique numbers. Hence, the first set is the same as the third, since both contain the numbers 1, 2, and 3. Now, how can you implement something like this in Python? I have my little Python console open down there. You could put it into the console just like we did before. We can say 1, 2, and 3 with curly braces, and that's a set. We could also define an empty set by just having an empty pair of braces or a strike through 0, like so. So, empty pair of braces, so that's an empty set, or, which is the same thing, strike through 0. In Python, this wouldn't work so easily, since an empty pair of braces could represent a set or a dictionary. Hence, to create a set, we use the set keyword without any arguments. So we can say set, and that's an empty set. We can indicate that something is a member of a set by using the in operator. That looks a bit like an E. So we can say 2 is a member of the set 1, 2, and 3. So this says that the number 2 is part of a set containing the numbers 1, 2, and 3. In Python, we can literally use the in keyword. So we can say 2 in 1, 2, 3, and returns true. So this will yield a Boolean value in return, indicating that the number 2 is indeed a member of that set. Likewise, we indicate that something is not part of a set by using the not in operator. That operator is the same as the in operator, but strike through. So we can say, for example, 5 is not a member of the set 1, 2, and 3. In Python, you can put the not keyword in front of the in keyword, which will negate the Boolean result. So we can say 5 not in 1, 2, and 3, and that is true. Sometimes the roles can also be reversed, and you will see that the set first and then the element with a mirrored in operator. This is the contains operator, and you can read it exactly as it says. So we can say the set 1, 2, and 3 contains the number 2. So this says that the set contains the number 2. In Python, this amounts to another in check. Hence, there's no need for any new syntax, since it basically means the same thing. If there are a bunch of numbers in your set and there's a clear logic, you can shorten it with dots. So for example, if we want to get the numbers from 1 to 100, we can say 1, 2, 3, ... 100. However, we can also build such a set interactively like so. So we can say curly brace, and we can say x, which is a member of this special z set. And we're going to say that x is greater than or equal to 1, and it's less than or equal to 100. closing brace. Okay, so that is a big one. So let's digest this. The surrounding braces tells us that we are looking at a set. So whatever is inside the curly braces, it will return a set. So the first part says, so this part right here, so this part right here, it says that X is in the set of Z. This big Z is a special set which represents all the integers. This is an infinitely large set since it contains all the possible whole numbers. However, there's a logical condition saying that X must be greater than or equal to 1 and less than or equal to 100. Okay, so it's all the numbers that are whole numbers that are between 1 and 100. And this is exactly the set we have described before. So using this set builder notation, we can logically define our set. If you are familiar with list and set comprehensions in Python, this should look very familiar to you. So let's first create a set, Z, that ranges from minus 999,000 to 999,000. And then we're going to do a set comprehension saying X for X in Z if X is greater or equal than 1 and X is less than or equal to 100. So, and there you go. And here you have all the numbers from 1 to 100 in the set. So here I first create a set of all the integers between minus 999,000 and 999,000. Our computer can't really save an infinite amount of number since there are some memory constraints at place. However, there are much more numbers in that set than we actually need. Okay, so next we create a set comprehension. So down here, this is a set comprehension. First, we define what we do with our number. And here we're just taking it. So we say for every X, we just take X. Then we define where we actually take it from. So we take it from this set called Z. Then we also define a filter on X. This is pretty similar to the set builder notation we have seen before. You can also relate sets to each other. So for example, if two sets are equal to each other, you can just state this equality. You can say A equals B if both are the same set. In Python, we can create two sets and check the equality with two equal signs. Note that one equal sign binds a value to a variable, while two equal signs is an equality check. So we can say A equals 1, 2, and 3, B equals 3, 1, 2, and 1, and then we can say A equals B, which returns true. So the last expression is true since sets are unordered and unique numbers. Since both sets contain the same unique numbers, they are the same. If all the members of a set A are also in B, we say that A is a subset of B. Mathematically, you would use the C-looking character with a little bar underneath. So we say A is a subset of B. The bar might also be missing. So note that A and B don't have to be the same set. If you want to emphasize that A is a subset of B, but it's not equal to B, you can leave out the bar at the bottom. In Python, you can use the isSubset method on a set and give it another set. This will tell you whether one set is a subset of the other. So we can say A equals 1 and 2, B equals 1, 2, and 3, and then we can say A is subset B, and this returns true. So this returns true since the number 1 and 2 are both part of the set B, which also has the number 3. The superset switches the check around. Here we say that all the elements of A are also in B. A superset B. In Python, you can use the isSuperset method. If we use the same values from before, it should return false since A is missing the number 3 to be a superset. So we can say A is superset B, and this returns false. If you want to combine two sets, you can union them. The result from getting the union of two sets will be the numbers that are contained in either set. For that, you use the U-looking character. So you say A union B. Use the union method on a set in Python and enter a second set. It will return the numbers of either set. So we can say A equals 1, 2, and 3, B equals 2, 3, and 4. And we can say A union B, and this gives the set 1, 2, 3, and 4. As you can see, it's all the numbers from either set. Now, what if you only want to keep the values that are literally in both sets? So for this, you'd use the intersection operator, which is the union operator turned on its head. So you can say A intersect B. Python sets have the intersection method for this one. Just as before, it accepts another set as an argument. So we can say A equals 1 and 2, and B equals 2 and 3. And then we can say A intersection B. And this returns a set with the number 2 in it. So since only the number 2 is in both sets, the result set will contain only this single number. You can also take one set and remove from it all the numbers that are in another set. This you can write as a simple mathematical operation. So you can say, take the set 1, 2, and 3, and from it we subtract the set 2 and 4, and this will return the set 1 and 3. Since the number 2 is in both sets, we remove it from the first set. Having the number 4 in the set we use for the subtraction does not have an effect since it isn't in the first set. So let's switch to Python to implement the same calculation. So we say 1, 2, 3 minus 2 and 4. And there you have the set 1 and 3. You can get the length of a set, which is the number of unique numbers inside the set, by putting pipes around the name of the set. So if the set is A and it has 3 elements, the cardinality of A will be 3. So we can say A is equal to 1, 2, and 3. Then we say the cardinality of A, by putting pipes around the name of the set, that one is equal to 3 because there are 3 numbers in there, or 3 unique numbers. You can use the len function for that in Python. If you give it a collection as input, it will return the number of elements in that collection. So we say A equals 1, 2, and 3. And then we say len A, this returns 3. Also, you might already know what a cross-join is. There's an equivalent in sets, which is called the Cartesian product. It's the combination of every element in A with every element in B. So if you say, for example, A is equal to 1 and 2, and B is equal to 3 and 4, then when we say A x B, this is the big multiplication operator. This will be the combination of every element. So 1 and 3. Then we're going to have 1 and 4. We're going to have 2 and 3. And we're going to have 2 and 4. Okay, so let's move away from sets from now and let's go to lists. Lists and sets in math are exactly the same in Python. While a set is a collection of unordered and unique numbers, the list is a bit more relaxed in that regard. It's an ordered collection of numbers. You declare a list with parentheses and the members inside. So you can say A equals parentheses 1, 2, and 3. In Python, you create a list with a pair of square brackets and the members inside. You can also use parentheses to create a tuple. However, notice that there has to be at least one comma inside the tuple because it's actually the grouping using commas instead of the pair of parentheses that declares the tuple. So let's create a list. First, and the list is going to be square brackets 1, 2, and 3. So notice the square brackets here. That's a list. So let's create a tuple, which is open parentheses 1, 2, 3. And we can check the type. So we say type A, that is a list, and type B, that is a tuple. Usually we want to work with the data inside the lists. This is where the big operators come in. This is also where people usually start to get scared since they look a bit daunting. But basically all they do is represent one of the basic math operations on every element of a list. So for example, there's the sum symbol, which has a start and an end index like so. So the operator looks a bit like this, and it has a start, and let's assign that to j, which is 1, and it has an end, which is 5. And then we also need to run an operation on that. And let's raise x to the jth power. And this is nothing else than x to the power of 1 plus x to the power of 2 plus x to the power of 3 plus x to the power of 4 plus x to the power of 5. Okay, so how do we actually read this? So first of all, the capital E looking symbol, that's the sum operator. So this right here, this is the sum operator. It has a start index at the bottom. So right here, that's the start index, j equals 1, and an end index at the top. You can see that it starts at the number 1 and that it ends at the number 5. We iterate through all the numbers from 1 to 5, and during every step of the iteration, we assign the number to j. Obviously, we also need to do something with that number, and this is what follows after the sum symbol. We use j by raising x to the power of whatever j is, so x to the power of j. Remember that this is the sum operation, hence we sum the result of every step, like on the right-hand side of the equation. So in the first iteration, it's j is 1, so it's x to the power of 1. Then the next step, and we got to sum it, so we add a plus sign. J is 2, so x to the power of 2. Then we sum this again, plus, and then the third step is j is equal to 3, x to the power of 3, and I think you get the idea. So does this look kind of familiar in Python? If you're thinking of a for loop, you're absolutely correct. We loop over all the numbers from 1 to 5 and raise x to that power. We then add that number to some global sum. So let's implement the exact same in Python. Now obviously I need to set x to something, so let's just set x to the number 2. So x is equal to 2. Initialize the sum, and I'm going to call this sum num, because sum is a special character, and then initialize this to 0. And I'm going to say for j in range 1 to 6, I'm going to cover that one, colon, and then we actually need to run our code. Well, what do we want to do? We want to take sum num and add to it x to the jth power. Let's run this, and let's print sum num. And it's 62. So what are we doing here? So first I set x to 2. This is just a random number that I come up with because, well, I need to give it some number. Afterwards, I initialize a sum and set it to 0, which is a reasonable starting default value. Then comes the interesting part. I range from 1 to 6. The starting index is inclusive, the ending index is exclusive. Hence, if you want to range from 1 to 5, you need to set 6 as the ending index. A bit cumbersome, but that is the way it's implemented. Afterwards, we increment the sum by whatever x to the jth power is. So in other words, the number 2 to the jth power. There is also an equivalent for multiplication, and it looks a bit like this. Doesn't look super nice, but it gets the job done. So let's start with j equals to 1, and let's end at 3. And the operation that we want to run is, let's say, x plus j. And this is then nothing else than x plus 1 times, because we're doing multiplication here, x plus 2 times x plus 3. And that's it. Again, I am looping from a start to an end and assign whatever index we are currently at to the variable j. Instead of summing every subresult, we are multiplying every subresult. So let's implement this in Python. Again, we are going to use a little loop. However, instead of adding something to the product, we will multiply the product with something. So let's set x to 5. Again, I just need a random value here. And let's start the product with 1. So we're going to initialize it to 1. And then we say for j in range 1 to 4, because we want to range from 1 to 3. And remember, the ending index is not inclusive, colon. And then the actual operation that we want to do, well, we want to take the product and we want to multiply this with, and then assign to it, to product again, whatever x plus j is. This is going to be our operation. And let's have a look at prod, which is 336. So notice two things here. I initialized the prod with 1 instead of 0. If I would initialize it with 0, the end result would also be 0, since we would multiply something with 0, which yields 0. Also, notice how we use asterisk equals instead of plus equals. Hence, we are multiplying the prod with whatever is to the right of the assignment operator. So this should be enough for you to navigate through collections and operations on such collections. Okay, next on, we will work through logical notation. In Python, we do use logic quite a bit. For example, when we say something is true, or when we chain together logical expressions with conditions. You can do the same in math. So let's start with the three most important logical operators, and, or, and not. If you have two conditions that can either yield true or false, you can combine them with the caret character, like so, to indicate an and condition. So you can say, for example, p and Q. If both are true, the resulting expression is true. If any of the two is false, the resulting expression is also false. When implementing this in Python, you can use the literal AND keyword like so. So you can say true and false. And this, obviously, the expression results in false, since the second part is false. If you use the OR character, which is the AND operator turned on its head, at least one of them has to be true for the whole expression to yield true. So we can say P or Q. Python has the equivalent OR operator. So we can say true or false, which returns true. So this returns true since the first value is actually true. And that's already enough. You can negate a logical value using the NOT expression. Putting a NOT before something that is true makes it false and vice versa. Hence, if Q is true, the following expression is false. So we can say not Q. And Python uses the corresponding not keyword like so. So we can say not true. And obviously this negates true, which is false. If you want to describe a causal relationship, you can use an arrow. If you want to say something like if A, then B, you can describe it like so. So you can say if A, then B. More formally, we say that A implies B. Python allows us to model such a behavior using an if condition. We can put the logical check after the if word, and then whatever we put in the body or block of that statement will execute. So if you say A equals true, we can say if A, and only then we want to print A is true. And it prints A is true. You can also make the relationship go both ways by using the if and only if operator, which is an arrow that goes both ways. So something like this. Also, if you read mathematical proofs, you might also be interested in the following symbols. However, I will not provide a Python example for this, since mathematical proofs are not about concrete calculations, but more about abstract thinking. So if you want to reach a conclusion, you can use 3 dots as a triangle. This stands for therefore. So you can say something like this. So therefore, x is greater than 0. If you invert the triangle, it will stand for because. So you can say because x is not 0, so something like this, because x is not 0. And often in proofs you want to show a contradiction. And if you believe to have found a contradiction, you can indicate so with 2 arrows pointing at each other. So you can put in something like this. Once you are done with your proof, you can drop a square to indicate that you are done with your proof. So you can literally just drop a square. Also, you might see it filled out. That's also possible. So quantifiers are also very important in logic. So maybe something holds for all the elements or only for certain elements. And this is something you want to specify. If you want to quantify all, you can use something that looks like an A turned on its head. So for example, if you want to say that for all numbers, the square is greater than 0, you can do it like so. So you can say, use this A that it's turned on its head. So every x that is part of the set of, and this is the set of real numbers, comma, the square of x is greater than or equal to 0. So for all the x that are part of the set of the real numbers, x squared is greater than or equal to 0. So I agree that this is a bit complicated to read, but if you look at it piece by piece, it's not that complicated. So remember that the rotated A means for all. Then we simply add an x, reading like for all x, and then we see the set membership again. This R character is a special shorthand for all numbers on a number line. So first thing is we're going to set up a range of numbers. So from minus 100 to 100. And we're going to say non-negative is equal to true, because this is what we are going to check. Then we say for every x in data, what we're going to do is if the square root of x is less than 0, so if it's negative, then what we're going to do is we're going to set non-negative to false. So if there's at least one negative number, non-negative will be false. So let's see what non-negative is. So let's print non-negative, and it's still true. So what I do is I create a list from values from minus 100 to 100. Again, in math, we're dealing with an infinite set, but what we are doing generalizes to infinity here. So I also set a Boolean variable that will tell us whether all the values are positive. I initialize this as true. Hence, we assume that all the values will be positive in our later calculation. Next, I loop over every element in the data list. I check whether the square root of the element in the loop is negative. If so, I set the non-negative variable to false. Finally, when we print the non-negative variable, you can see that it is still true. Hence, there was never a situation where the square of x is negative. You can also use list comprehension to make this look more like a mathematical statement that we had before. So first the list comprehension. So we say pair of square brace, because that's the list comprehension. X to the power of 2 greater than or equal to 0 for every x in the range from minus 100 to 100. And we want to check that all those values are true. So we can say all parentheses and use the list or the result of the list comprehension as an argument, and this returns true. So let's start from inside of the list comprehension. For every x in the list of numbers ranging from minus 100 to 100, we first raise it to the second power. Then we check if that value is greater than 0. This creates a list of Boolean values. True if the number is positive, false if not. The all function returns true if all the elements of that list are true, and false if there is at least one false value. This translates nicely to the statement we have seen at the beginning. There's also an equivalent that is less strict, that simply states there exists something with the mentioned condition. You would use a mirrored e for that, like so. So you could say mirrored e. So there exists an x, which is part of the set of real numbers. So let's use the same set, where x to the second power is equal to 4. So this simply states that there is a number x in the set of real numbers, or basically saying it literally says there's a number x that if you square it, it will be equal to 4. So let's do the same in Python, and I will first show the long approach and then the same thing using list comprehension. So we're going to create a range of data from 0 to 10. Then we're going to initialize equal 4, and we're going to set it to false. So we're going to start with false here, and then we say for x in data, do the following. If x to the second power is equal to 4, then do the following, set equal 4 to true. And then let's print the value of equal 4, and this should be true, and it's true. So as promised, it works, and obviously the number 2 did the trick. The way we go about it is very similar to the way we did it before. I first create a list of numbers, initialize the Boolean value for something being squared equal to 4 to false, then loop over all the numbers in that list of numbers, raise the value to the second power, and if that value is equal to 4, I set the equal 4 value to true. So let's do the same thing using list comprehension. So let's start with the list comprehension first. So we say x to the second power equal to 4. So this will return a Boolean value, either true or false, if x to the second power is equal to 4 for every x in the range of 0 to 10. And let's close the list comprehension, and we're going to put this as an argument to the any function. And this one is true. So any checks if any of the values in a list of Booleans is true. Since we know that there is one value, it returns true. Using the all function would obviously return false. If you want to emphasize that there is literally only one number that fulfills the condition, you can add an exclamation mark right after the mirrored e, like so. So you can say there exists exactly one number and only one number, and we make sure that it's only one number by putting this exclamation mark here. So x, which is a member of the set of real numbers, so we had that already before, where if you square it, it's equal to 0. So here we say that there's only one number that if you square it, it will be equal to 0. Obviously, that is the number 0 itself. Everything else that you square will be different from the number 0. Let's start talking functions. Functions are the lifeblood of math and programming. In math, it represents something like a mapping. For a given tuple of inputs, it maps to a certain output. For example, if a function takes an input value x and produces an outcome value y, given the same x, it will always produce the same y. On a very basic level, you can say that there's a function f that takes a number as input and produces a number as output, like so. What this says is that there is a function f that takes a real number as input and produces a real number as output. You can also generalize this more and say that the function takes a value from set A as input and produces an output from set B. In Python, this doesn't look too different. Let's say we create a function that adds the number 2 to an integer. We can write it like so. Def add 2, x, which is an integer, is the input, and it creates one output, which is also an integer. And it returns x plus the number 2. So we are defining a function called add2. So the f part from before becomes add2 here. It takes exactly one input that we call x. The typeint says that x should be an integer. After the argument parameters, we also say that the function returns an integer. The actual body of the function is not that interesting. However, notice the notation, int in, int out. The function notation that is a bit more common is something along the lines of y equals f of x. This means that we put x into a function and it produces some output y. Sometimes this also gets abbreviated with a little arrow. However, notice the little back pipe of the arrow. So we can say x, and then we put in a little arrow, y. That is the maps to character. Remember that I told you that all functions do is map the arguments to some output. Same input, same output. Same here. It says that some value x maps to some value y. If you want a similar looking implementation in Python, you would use a lambda expression like so. So we can say f equals lambda x colon x plus 2. And let's call this function with the number 2 as input, and we get the number 4 as output. So it's the same function as before, but it's an anonymous function. Lambda functions are good for small packaged functions that don't contain a lot of logic. Maybe a word of caution regarding the comparison of functions in math versus functions in Python. Remember that I told you that mathematical functions always produce the same output for the same input. While this is also true for the add2 function that we have defined before, that is not always the case. In Python, when a function always produces the same output for the same input, and it doesn't do anything else than producing the output, we call it a pure function. However, you can also have unpure functions that don't produce the same output for the same input because they depend on something else. Maybe they read some data from a database or from disk. Hence, they're dependent on some state, which makes them unpure. Okay, let's talk about piecewise defined functions. Normal functions implement the same logic no matter what you give it as an input. For example, the function x to the second power always squares x, no matter what x is. However, you can also define separate logic depending on the input value. So here's an example where we return the logarithm of a function if the value is positive. Else, we simply return the number 0. So we can say f of x, so this is our function, is equal to, and then we have this curly bracket, log of x, if x greater than 0, or the number 0 otherwise. In Python, this boils down to either one of the following two approaches. You can either use an if condition and then define the logic inside the body of the if condition. Alternatively, if you have a more recent version of Python, you can also use a k-switch statement. I'm going to show the if statement since this is a more widely understood concept in my opinion. So I'm going to import something. I'm going to say import math. So I need the math package. I say define f of x, and x is an integer, and it returns an integer. If x is greater than 0, we are going to return, well, we're going to take the log function from the math package and I put x in. However, else I return 0. And I can also call it, let's call it on the number 4. Since the function from before is calculating a logarithm, I am importing the math package, which has a function to just do that. If you don't know what a logarithm is, that's fine. At this point, I just want to illustrate the piecewise function. Again, we are defining a function. It takes one input x, which I assume to be an integer. Also, the function returns an integer. Then inside the function implementation, I first check whether x is greater than 0, just like the first condition of the piecewise function. If that is true, I return the log of x. After this, we have an else condition that runs if x is not greater than 0. In that case, I simply want to return the number 0. Obviously, you can also use one function as the input to another function. So for example, assume that you have a function f that maps a number from set A to a number in set B. Then you might also have a function g that maps a number from set B to set C. So we have one variable, which we're going to call x, that we first push through the function f, and then take that result and push it through the function g. Something along the lines of this. So we have a function f, and it maps a number from set A to a number from set B. Then we have a function g, which maps a number from set B to a number from set C. And then we say y is equal to g of f of x. As you can see, on the right-hand side of the equation, it means the same thing. Just as in Python, the function needs to be read from within. So first we get the value that is being returned from pushing x through f. This number will then be the input to the g function. In the end, we assign this to the y variable. Since things can get very messy using nested notation, you can also write the function like this. So this is going to be the same as saying g, and then I'm going to put in a hollow little dot in there, f of x. So this is the same. So it's g, small hollow dot in there, f of x. As you can see on the right-hand side of the equation, it means the same thing. Read from right to the left. So we first push x through f, and then that result through g. In Python, it works the same as in math. If you have two functions and the output of one is the input to the other, you could run it through the first function, save the result to a temporary value, and then use that value as input to the other function. However, you can also add the function calling within the function calling of the other function. The functions are evaluated from inside to the outside. So we can say, let's create one called square, which takes one value as input, which we call x. It's an integer. It returns an integer. And all we do is we return x to the second power. So we can say y equals square 2. So we take the square of 2, but the output goes into the square root function of the math package. And then let's have a look what y is, and y is the number 2. So I first define a function to square a number, then I run 2 through the square function. That result will be the input to the square root function. Hence, y should be 2 again. Remember that functions can be seen as a mapping from a number in set A to a number in set B. You can also turn that around by running the inverse of a function. That is the function that will take y and bring back the x that you gave it. Hence, it's a mapping from numbers in set B to the numbers in set A. It is indicated with a little -1 in the superscript of the function. So if I have a function that I call y equals f of x, now if I want a function that I give y and it brings me back x, I call this the inverse. So the inverse is f -1 in the superscript of y. If you look at our previous function, the function raising x to the second power is our regular function. The function taking the square root of our function, that is our inverse. And that is because y is equal to, let's square x to the number 4. And let's print y. So it's 16. And if we take the square root of y, and we set it to x, and x is again the number 4. Okay, let's cover some very common functions and how they are represented in math. So first we start with the absolute value. The absolute value of a number is simply its value always positive. Although there is a more meaningful interpretation of the absolute value, for practical purposes, this is a good explanation. You simply put two pipes around whatever you want to get the absolute value for, like so. So if a is equal to minus 14, then the absolute value, so we put two pipes around, is the number 14. In Python, the absolute value can be implemented very easily using an if statement. If the value is negative, multiply it with minus 1 and return the result. Else you return the result as it is. So we can say def abs, and we're going to say x is an input. Let's say we assume it's an integer, and we're going to return an integer. And we say if x is less than 0, then return x times minus 1. Oh, sorry, return x times minus 1, else simply return x. And we can run it on, let's say, minus 14, like we did before, and we get back the number 14. There is also the square root, which you probably already know. And what you do is, if you calculate the square root of x, you get the number that you need to raise to the second power in order to get x. So the square root of x looks something like this. Important, make sure to pay attention what the square root actually covers, so the top part of it. It covers everything that is captured by the top bar of the square root. Since we have already used the square root function from the math package, there is no further introduction needed. However, I will show you an alternative. If you want to have the square root of something, you could also raise it to the half power. So we could say, let's define our own square root function, and it takes x, which is an integer, and it returns an integer. And what you can do is you can just take that x, and if you want to have the square root, you can raise it to the 1 divided by 2 to the half power. And actually, let's get the square root of 16, and it's 4. And you can generalize the root to any base. So for example, taking the cubic root of x is the number you need to raise to the third power in order to get x. Likewise, you can raise a number to the 1/3 power to implement the same calculation in Python. In math, you simply put a little number on the root to indicate what root you're actually calculating. If there's nothing, the square root is assumed. Here's how you would write down the third root or the cubic root of x. So you would say third root of x. So let's implement that in Python. So let's say cubic root of x, and we assume x is an integer, and we want to return an integer, and we're simply returning x raised to the 1/3 power. And let's do this with the number 64, which is 4. There's a little rounding error here. Sometimes you might just be interested in the sign of the number and not in the number itself. For that, you can run this signum like so. So you can say sign SGN 150, that is 1. The sign of O is O, and the sign of minus 64 is minus 1. It always returns 1 for positive numbers, 0 for 0, and minus 1 for negative numbers. It is basically the number you need to multiply the absolute value with to get the inverse of the absolute value function. So implementation in Python is easy by just using the else if statement, or elif. Since this is not just a simple binary check, we need to check for more than just two possible states. So let's implement this. So we can say def signum, so this is going to be a function, checks x as an input, and we're going to produce an integer output. So if x is greater than 0, what we are going to do is we're going to return the number 1. Elif, so else if x is less than 0, we are going to return the number minus 1. Else, so if both actually fail, we're going to return the number 0. So let's get the signum for 150, which is 1. Let's get the signum for the number O, which is 0. And let's get the signum for minus 64, which is the number minus 1. So we start by checking if x is greater than 0. If so, we return number 1. If the number is less than 0, we return the number minus 1. Else, and the only possibility left is that the number is exactly 0. In that case, we return the number 0. The examples from before check out as you can see. So let's cover the exponential function. It is different from the power function. While the power function takes a number x to the nth power, The exponential function takes a constant value to the x power. This is the exponential constant, which we write as a lowercase e. It is equal to approximately the number 2.718. This is somewhat of a magic number, as it turns out that many processes in nature can be modeled by raising this number to a certain power like so. So we can say exponential, and we raise it to the x power. And this is roundabout the same as saying 2.718 to the x power. Likewise, this can be implemented pretty easily in Python if we are fine with 2.718 being a good enough approximation for the exponential constant. So we can say def exp, this is going to be a function, takes an x as an integer, and it's probably going to return a decimal number. So I'm using a float as a return type. And we can do return 2.718 to the power of x. And let's run the exponential function with 4, which is 54.57. Closely related to the exponential function is the logarithm function. The natural logarithm is the inverse of the exponential function. Hence, it is like what the square root is to the power function. The natural logarithm is typically denoted with ln for natural logarithm. It is the power that you need to raise the exponential constant to in order to get x. So we can say the natural logarithm of raising the exponential constant to the number 5 is 5. Implementing the natural logarithm in Python without any dependencies is not straightforward, and I don't think you would get much out of it. So we'll just use the math package for this. So what we are going to do is we're going to first use the exponential function on the number 5, which produces 148, and we save this to the x variable. And then what we're going to do is we're going to say y equals, and then we're going to take the natural logarithm of that x value, and this should be 5. And there you go. So first thing we do is raising the exponential constant to the 5th power. Afterwards, we take the natural logarithm of that number. This brings us back the number 5. Hence the logarithm is the inverse of the exponential function. You can see in my code that the function just says log and not natural log. The same is true in math. You might see the natural logarithm being written as log. However, it doesn't have to be the natural logarithm because you can generalize this concept. The logarithm can take any arbitrary base. The function then returns the nth power to which you need to raise the base to. So for example, you can use 10 as a base. So you can say, for example, log with using 10 as the base for x. So this function calculates the power that you need to raise the number 10 to get x. Seems a bit complicated in words, but let's do this in a simple example in Python. So let's set x to the number 1000. And then let's calculate y as the log of x, but as a base, we're going to use the number 10. And this returns 3. So don't mind the rounding errors. This is just a quirk of computers. So first we set x to 1000. Then we calculate the log of x and set the base as 10. Hence, y will be the value we need to raise 10 to in order to get 1000. Of course, this is 3, since 10 times 10 times 10 is 1000. You can do that with any base and it would follow the same logic. I assume that you know how rounding works, but there's also the floor and ceiling. The floor basically returns the whole number part of a decimal. The ceiling also returns the whole number, but the floor plus 1. So we can say that the floor of the number 3.99, and don't forget the brackets with little feet down there, is equal to 3. If you want the ceiling, you would give it some arms instead of feet. So you would say the ceiling of 3.01 is equal to 4. As usual, let's do an implementation of these two in Python. So we're going to define the floor function, and it takes an x, which is going to be a decimal, so I say float, but it's going to return an integer actually. And what we're going to do is we're going to return the integer of x. So let's say floor 3.99, which is equal to 3. This basically just deletes the decimal part, which is what the floor function should do. We can actually reuse the floor function in our ceiling function, since the ceiling function can just add 1 to the result of the floor function. So we can say def ceil takes a float as an input and returns an integer. And all it's going to do is we're going to return whatever the floor of x is plus the number 1. And we can say ceiling of 3.01, and that is 4. Now, if you ever venture into functional programming, I can guarantee you that you will stumble upon the factorial. The factorial is a function that takes a number n and then multiplies it with itself minus the number 1, n times. This is actually easier to write down than to explain. So let me do just that. Note that the factorial of a number is indicated with an exclamation mark like so. So n factorial is n times n minus 1 times n minus 2. And this goes on and on and on until we say times 2 times 1. So maybe one concrete example. 4 factorial is simply 4 times 3 times 2 times 1. I think the concrete example of 4 factorial is the best explanation of how it works. Now, how would we implement something like this in Python? If you haven't done functional programming before, you might think that this can be done with a loop, and you would be correct. However, let's spice things up a bit and do a different implementation of it. As you might already know, Python functions can call themselves, and we can actually use this property to implement the factorial function like so. So we can say def factorial, and it takes n, which is an integer, and it's going to return an integer. So if n is equal to 1, we return the number 1, else we're going to return whatever n times the factorial of n minus 1 is. And it's called factorial 4, which is 24, which is same as 4 times 3 times 2 times 1. Okay, so what is happening here? So let's start with the function signature. It takes one input n and it returns an input of the same type. Well, this seems reasonable since one number was also enough input for the factorial there. So looking inside the function, we start with something odd. We say that if n is 1, we return the number 1. Let's get back to that later actually. If n is not 1, we simply return n times the same function, but we decrement the value of n by 1. This makes sense. It's exactly what the function said it would do, right? So what we have written here is a recursive function. A recursive function is a function that calls itself. And when you write them, you usually start with the end condition. You catch the point where you want to stop calling itself. That is what we are doing with the if n is equal to 1 check. If it is equal to 1, we stop the whole thing and we return the value 1. Then comes the recursive part, where the function just calls itself. The way this gets executed on a computer is that it will defer all the calculations in between and start with the last one. The last calculation in the recursive chain will be evaluated first. So the reason for that is that your computer will put the function calls on a stack. Just like with dishes you put on a stack, you will retrieve the latest one first. And that one has an actual value, which is the number 1. For the second to last function call, we know that n was equal to 2. And we know that the value we multiplied with is 1. Hence, it is 2. Then the third to last call here, we know that n is equal to 3. And that the factorial of the call before is 2. Hence, 3 times 2 is 6. Then, for the first time the function ran, we know that n was 4. And that the factorial of n minus 1 is 6. Hence, the final result is 4 times 6, which is 24. So if you don't grasp the concept, I can totally understand. It's a bit odd at first, but for many problems, recursive calls are actually a very elegant way to solve a problem. If you don't like the implementation, let's do it with a simple loop. So let's clear the screen. So we say define factorial loop n, which is an integer, and it returns an integer. And we're going to say, well, prot is equal to 1. And then we say 4x in range 1 to n plus 1, so whatever n is. And we're going to take prot and assign to it whatever prot times axis. And then we return prod. So it says this factorial loop n equal to 4, 24. So we start with initializing some product, which we set to 1. Then 1 ranges from 1 to n. Remember that I set the ending index to be n plus 1, since the ending index is not inclusive. Here we multiply the product with x. In the end, we then simply return the product. While there's certainly much more notation when it comes to functions, this should get you started pretty good. Let's enter the exciting field of linear algebra. Since linear algebra comes with its own set of notation, it's good to spend some time on it. As you probably know, the most basic building block of linear algebra is the vector, which is simply a collection of elements. In that regard, it is very similar to the list. You can either have a row vector or a column vector. The row vector has the numbers in horizontal format, while the column vector stacks the numbers vertically. Hence, you would write them like this. So if you would have a row vector, you would say something like A equals x1, x2, x3. This is a row vector. Notice how the variable a, which represents the row, is in bold letters. By convention, variables that are bold and lowercase letters represent vectors. Let's also create a column vector. So we can say b, and that one is equal to x1, x2, and x3. Sometimes the variables that represent vectors are also written in regular lowercase letters, with a little arrow on top on it like so. So you might have a vector that looks like so. I think this notation is rather common in physics. However, in statistics and economics, it's more likely that you will see a boldface lowercase letter. Creating vectors in Python is very simple. You can basically just create a list with the elements inside. That will be a row vector. For a column vector, it's a bit more involved, since every element of the list would be another list that holds the row. In this case, there would be only one member each. So let's look at it. So we can say A, which is a row vector, would be list of 1, 2, and 3. Then let's create a column vector. So it's a list of lists. So first column, second column, third column. So notice a small difference in notation between math and Python. In math, the elements of a vector are separated by some white space. In Python, you need to explicitly separate them with a comma. The row vector is pretty straightforward. The column vector takes some time to get used to. However, this will make more sense once we have covered another essential element type in linear algebra, the matrix. However, for now, let's stick with vectors, and whenever I talk about vector, think about row vectors, which makes it easier to grasp. You can do regular math with vectors. For example, you can do vector addition, which just adds each element of the two vectors at the same position. And you can do it like so. Let's say we have two vectors. First vector is the elements 1, 2, and 3. And to that, we add a vector with elements 4, 5, and 6. And this results in another vector with the elements 5, 7, and 9. Because 1 plus 4 is 5, 2 plus 5 is 7, 3 plus 6 is 9. In Python, we need to loop over both lists and create a new vector to run this calculation. So let's define this function. So we're going to define vector addition, where A is a vector, so it's a list of integers, and B is also a vector, so it's also a list of integers. And it's going to return another vector, which is also just a list of integers. So first thing we do is, if the length of A is not the same as the length of B, we're going to raise a value error saying length of vectors must be the same. Then what we're going to say is vector new. It's going to be an empty list. Then we say for y and z in zipping A and B. What we will do is, to this vector new, we will append the sum of y and z. Then in the end, we just return this new vector. So let me run the one calculation. So vector addition, we're going to run this on vector A, is going to be 1 and 2, and vector b is going to be 3 and 4. And this yields a vector with 4 and 6. So there are multiple ways to implement this. However, every implementation first should check if both vectors have the same number of elements in it. After the check, I initialize the vector that will hold the element-wise addition of both vectors. Notice that this vector starts out empty. I then proceed to populate the vector by looping over two elements at the same time, y and z. If you use the zip function on two collections, it will return the two elements at the same position of each collection. And you can loop over it. Y will be the element from the A vector and Z will be the corresponding element from the B vector. I then simply append to our new vector the sum of these two variables. In the end, I return the new vector to the caller. So this would be a bit more tricky if we would work with column vectors, since every value will be another one element vector, but I think this suffices to demonstrate the logic of the operation. You can also multiply a vector with a single number. That is called the scalar multiplication. What you do is you multiply every element of a given vector with that single number. So you can say r times the following vector, 1, 2, and 3. And this will basically be the same as saying 1r, 2r, and 3r. The implementation of this in Python is pretty straightforward, since we can just loop over the elements of the vector and apply the multiplication. So we can say find scalar multiplication, and it's going to take a scalar value, which let's say is integer, and it takes a vector, which is a list of integers, and returns a list of integers. Okay, and all we're going to do is we're going to say return. I'm going to use a list comprehension. I'm going to say take the scalar times x for every x in the vector. And we immediately return this to the caller. So let's try this out. Scalar multiplication, and scalar is going to be 3, and the vector that we want to use is going to be 1, 2, and 3. Let's call this, which returns 3, 6, and 9. So this time I choose a pretty simple implementation by running a list comprehension. I simply loop over every element in the vector and multiply it with the scalar, just as I said. So what if you want to get the magnitude of a vector? And this time I don't just mean the number of elements in it. I'm talking about the geographic length of a vector. Obviously, the magnitude of a vector is correlated with the actual numbers it holds. The smaller the numbers inside the vector, the smaller the vector itself. You would represent the magnitude of a vector with two bars on each side like so. If we have, for example, two vectors, so A is 1, 2, and 3, and B is 100, 200, and 300, then we could say that the magnitude of B, let's make this bold, is greater than the magnitude of A. So what I'm saying is, in the last part, it's the magnitude of vector B that is larger than the magnitude of vector A. Although both have the same number of elements, the magnitude of values in B is much bigger. There is also a formula for calculating the magnitude of a vector, and it goes like this. So if you have a vector x, then the magnitude of that vector x is equal to the square root of x1 squared plus x2 squared plus dot 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 plus xn squared. So what this means is to calculate the magnitude of a vector x, you simply sum the squared values of all vector elements and then just take the square root of that sum. This gives you the magnitude of a vector. And you can implement it in Python like so. Let's say def magnitude, and as input takes a vector, which is a list of integers, and returns one integer, so one value. So let's initialize sum of squares, which we set to 0. I'm going to say for every x in that vector, so for every element in the vector, we're going to say sum of squares is actually, we're going to increment that one by whatever the square is. And then we say the magnitude is equal to whatever the sum of the squares is. And from that, we take the square root. And then in the end, we're going to return that. So let's run the magnitude on the smaller vector, 1, 2, and 3, which is 3.74. And let's run the magnitude on the larger one, which is 100, 200, and 300. And that one is 374. The function we define just takes a single vector as input, as we want to calculate the magnitude only for a single vector. Then, the first thing I do is I initialize a value for the magnitude and set it to 0. I then loop over every element of the vector and add to that sum the square of the element. To calculate the magnitude from that value, I take the square root by raising the number to the half power, which corresponds to taking the square root. You can see by comparing the two vectors for which we calculated the magnitude that the second one is much larger than the first one. There is also a second way to calculate how large a vector is, which is the p-norm. The p-norm is indicated by putting a small p in the subscript after the last pipe. The p stands for the power to which you raise the individual absolute values. So you can say, again, it's going to be magnitude of that vector x, so that's still the same, but in the subscript we put a little p in there. And that is equal to the absolute value of x1 to the pth power, and to that we add the absolute value of x2 to the pth power, then dot dot dot, all the way to the absolute value of xn to the pth power. And then we raise that to the 1 over p power. So that we take the pth root. So while this looks rather complicated at first, it's actually pretty easy to read. Note that we are grouping all the additions into a single group indicated by the parentheses. For every element in the vector, we take its absolute value and square that. Then we take this sum and calculate the pth root of it. If p is equal to 2, that's the same as the magnitude that we've calculated before. You can implement these calculations in Python like so. So we can say def p-norm, and as input we take a vector, which is a list of integers, and p, which is an integer itself. And we're going to return a float value, so it could be that it's decimal. So we're going to say sum of the absolute values is 0. Then for every value in the vector, what we are going to do is we're going to take the sum of the absolute values and we're going to increment that one by the absolute value to the power of p. Then I'm going to calculate the norm, which is just this sum of the absolute values to the 1 over p power. And then I'm just going to return that one. All right, so let's run the p-norm on our vector 1, 2, and 3. And for that, we use p equals 2. So again, this is 3.74. We had that before, but let's also run the p-norm for the same vector, but we're going to set p to 3, which is 3.3. And if we set it to 4, it's 3.14. So note that this function takes a vector and a value p for which you want to calculate the p-norm. We first initialize the sum of absolute values to 0, then we loop over the elements in our vector and add to the sum of absolute values the absolute value for the value in our loop, raised to the pth power. In the end, we take the final sum of absolute values and take the pth root of it. This is the value we want to return to the user. If you ever had a linear algebra class, you probably already know that multiplying two vectors is not equal to the element-wise multiplication. You multiply the single elements and then add all of these numbers together. This is called the dot product and is indicated by, and there's no surprise here, a small dot. So you can say x dot product with y, so these are two vectors, is the same as saying take x1, so the first element in the x vector, multiply that by the first element in the y vector, and to that product you are going to add the second element in the x vector times the second element in the y vector. Then dot dot dot, and you do this all the way until the nth element in the x vector and the nth element in the y vector. If we are really strict here, I should mention that you can only multiply row vectors with column vectors and vice versa. However, since you can easily transform a row vector to a column vector and the other way around, you can also indicate a dot product of two row or two column vectors. It's assumed that the necessary transformation is done before that. Let's now build a Python function that can multiply two vectors with each other. Again, technically one has to be a row vector and the other would have to be a column vector. However, for this implementation, we can just multiply two row vectors, although it's technically not correct. Why that is becomes more apparent when we talk about matrices. So let's say def, and we're going to say dot product, and it takes v1, which is a vector, so it's a list of integers, and we say v2, which is also a list of integers, and returns an integer. So we say if the length of v1 is not the same as the length of v2, well, then we're going to raise an exception here. We're going to say length of both vectors is not the same. Okay, other than that, we say sum of the prods. We set that to 0, and we say for x and y in zipping those two vectors. So we're gonna loop over the elements pairwise, say take the sum of the prods, and add to that the product of x and y. So we're gonna add x and y. And then we're going to return the sum of the prods. All right, let's run the dot product function on, let's say, the first vector is going to be 1, 2, and 3, and v2 is going to be 4, 5, and 6. Oops, there was an error there. Product. And it's 32. Since we are calculating the dot product between two vectors, we obviously have to handle two vectors as input. The first thing we check inside the function is that both vectors are of the same length. Afterwards, we initialize the sum of all the element-wise products to 0. I then loop over the elements that are in the same location in each vector by using the zip function on both vectors. Remember from before that this returns two values during every iteration. The first value will be from the first vector and the second value will be from the second vector. For these two values, we calculate the product and then add that to the total sum of all the products. In the end, we return this single number to the user. Have another look at the function signature. We don't return a vector, we return a single number. Another important concept when talking about vectors is the concept of orthogonality. If you know a bit about linear algebra, you know that vectors are pretty much geographical elements in space. If you have two vectors with two numbers in each vector is a line in two-dimensional space. So if we have, for example, so we're going to draw this graph, and then let's say our first vector goes 2 here, and then maybe 3 up. That's our first vector. And then maybe our second vector goes 1 to the right, and maybe 1 up. That's our second vector. Now, two vectors are orthogonal to each other when they meet at a right angle. So they will look something like this. This is our first vector, and this is our second vector. So two vectors are orthogonal to each other when they meet at the right angle. So these two vectors are orthogonal to each other. So there are two very interesting properties. First, although we cannot draw it, this idea of orthogonality extends to higher dimensions. Second, there's a simple calculation we can do to check if two vectors are orthogonal to each other. If the dot product between two vectors is 0, they are orthogonal to each other. You can indicate that two vectors are orthogonal to each other by putting the t, which is turned on its head, in between them like so. So if we have two vectors, let's say x and y, so if these two vectors, and we want to indicate that they are orthogonal to each other, we can indicate it like this. And this is the same as saying that the dot product between both of them is actually 0. As you might be able to see, the two lines of that rotated t are also orthogonal to each other. And you can see that many of these symbols actually, they make a lot of sense. In Python, we can build a simple Boolean function that returns true if two vectors are orthogonal to each other. We're going to reuse the dot product function from before. So we can say, let's create a function called orthogonal, and it takes one input vector, which is a list of integers, and another one, which is also a list of integers, and it's going to return a Boolean value. So we are going to first calculate the dot product. So we're going to say dot product of v1 and v2. And then if the rounded value of the dot product to the 9th decimal, if that one is equal to 0, then what we're going to do is we're going to return true. Else, we're going to return false. And that's it. So let's run this function on orthogonal. So the first pair of vectors we check are actually two orthogonal vectors. So our first vector goes none to the right and 2 up. And our second vector goes 2 to the right and none up. So these two vectors are orthogonal to each other, and it returns true. Let's do another check. So first one is going to be, let's say, 1 to the right, 1 up, and the second one goes 3 to the right and 4 up. So these are not orthogonal to each other, and it returns false. Again, the function takes two vectors as input. However, this time we are not returning a single number, but a boolean. It will be true if the two vectors are orthogonal to each other and false if not. Then the first thing we do is calculate the dot product between the two vectors. This shouldn't be new since we just defined the function before. Then follows something interesting. You might know that computers are notoriously bad at computing decimal values. So even though a calculation might return 0, due to some tiny rounding errors, it's not exactly equal to 0, somewhere deep within the decimals. Hence what I'm doing here is I check the number rounded to the 9th decimal place and whether that number is equal to 0. In this case, I say that the 9th decimal place is enough precision for me. If that number is equal to 0, I return true, otherwise I return false. Okay, on to the next big thing in linear algebra, which are matrices. Matrices are just collections of vectors, just like a table. It has m rows and n columns. You can say that you have a matrix of real numbers with m rows and n columns like so. So we can say set of real numbers, and into the superscript we put m rows times n columns. Just as easily you can say that you have a matrix of whole numbers with 5 rows and 2 columns like so. So set of integers, whole numbers, 5 rows, 2 columns. Here's a concrete matrix. Let's say we have 4 rows and 4 columns. You would have a grid of numbers with square brackets around. The variable that you assign a matrix to is usually a bold capital letter. So we would say something like m, and this is our matrix, is equal to, I'm going to put a few values in here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. And don't forget the square brace. So let's create a matrix in Python. There are actually two ways you can represent this. We can either say it's a list of row vectors or it's a list of column vectors. Let's do a list of row vectors. So let's do this. So we say m is a list of lists. So first list is 1, 2, 3. Then the second list is 4, 5, and 6. Third list, third row, in this case, is 7, 8, and 9. And let's close that list. As you can see, it's pretty straightforward. A list of 3 lists. Each list is a row vector. If you think about it, vectors are just special forms of matrices. A row vector is a matrix with 1 row and n columns, while a column vector is a matrix with m rows and 1 column. You can pinpoint an entry in the matrix by defining the intersection of a row and a column. This is usually done by using I for the row number and j for the column number. If we take the matrix from before, we can say that we want to extract the value from the third row and second column. You could do it like this. So you could say, so we say m, and in the subscript we say third row, comma, second column. And that is third row, second column. It's this number, which is 10. Notice that this is different from where we start indexing in Python. In Python, we start an index from 0, while in math, we start at 1. Now, how would we go about it in our matrix with row vectors? Well, we first extract the row vector we want, and then the entry for the row like so. So we can say def extract element, and it takes a matrix, which is a list of lists of integers, and it takes a row index, which is an integer, and a column index, which is also an integer, and returns a single number. So what we do is we say, okay, extract the row, so from m, extract row -1, and I will explain this. And we say, okay, then extract the column from the row, which is row indexed by column -1. And then we say return whatever the column value is. So let's say M is our matrix and it has it's a square matrix with 2 rows. So first row is 1 and 2, and the second one is 3 and 4. And then we say, okay, extract the following element. So M is going to be my matrix, and we want to go into row 1 and get the second column. So this should return 2, since we go into the first row and second column, and it returns 2. So the function that I define takes a matrix M, which is just a list of lists holding integers. Then I also accept a row and column index. Both are integers. Then finally, I say that I will return an integer. Let's have a look at what is happening inside the function. We are first extracting the correct row from the matrix by extracting the element at the row index decremented by 1. This is necessary since I want to keep the property of starting the count at 1. Once I have the row that I need, I take the column element from it. Again, I make sure to start counting the index by 1. Similar with vectors, you can add 2 matrices of the same shape whereby all of the matching elements are added with each other. So we can say something like a matrix 1 and 2, and let's also use 1 and 2 for the second row. And to that, we're going to add another matrix, and it's going to be 2 and 4, and 1 and 1. And this will be equal to the following matrix, 3 and 6, and 2 and 3. Because 1 plus 2 is 3, 2 plus 4 is 6, 1 plus 1 is 2, 2 plus 1 is 3. Assuming that the shape of both matrices is the same, we can just loop over the rows and columns and sum both elements. So let's define our matrix addition. So M1 is going to be a list of lists of integers. M2 is going to be exactly the same. So we're going to have 2 matrices here. And actually what we're going to return is another list of lists of integers. So we're also going to return a matrix. Then first thing we do is we check that the number of rows is the same. So if the length of M1 is not the same as the length of M2, we are going to raise a value error. I'm going to say different number of rows. But if that works, we're going to initialize an empty matrix M3 and then say for I in range from 0 to whatever the number of rows is. So we're looping over the number of rows, or the row index. We're going to say, well, if the length of columns, or if the number of the columns in that row I is not the same in those 2 matrices, well, then what I'm going to do is I'm going to raise another value error. I'm going to say different number of columns. However, if that works, what we're going to do is we're going to initialize a new row, so an empty list, and then we're going to say for j in range 0 to the length of M1 I, so in that row. So we're going to loop over the column indexes. And what we say is, well, to this new row, append the following. Take M1, go into the ith row, jth column, and into that from the ith row, the jth column in the other matrix. So we're going to append that value. And then once we're done, we just say, well, to that matrix, just append the entire row. And then in the end, we are going to return that new matrix. So let's create a few matrices as inputs. So first one is going to be a row vector with 1 and 2, and another row vector with 3 and 4. So that's our first matrix. Second matrix is going to be a row vector of 5 and 5. And let's do 6 and 6. And then in the end, we're just going to add these two together. So M1 is going to be M1. M2 is going to be M2. Let's try this out. And it gives us a matrix with 2 rows and 2 columns. So 6 and 7 and 9 and 10. Well, that checks out because first row, first column, well, it's 1 and 5, which is 6. Then first row, second column is 2 and 5, which is 7. Then second row, 3 and 6. And the first column, which is 9. And then the last column, 4 and 6, which is 10. Okay, so this implementation is a bit longer, but still manageable though. So let's dissect what is happening here. It takes two matrices as input and it returns one as output. The first thing that we do is check if the number of rows in both matrices matches. If they don't, we raise an exception stating so. Then I initiate an empty list, which will represent the output matrix. I call that one M3. We then start looping over the row indexes in M1. Remember that I assume that M1 and M2 have the same number of rows. If the number of columns in that row of both matrices doesn't add up, I raise another exception. Else I can assume that the number of columns in that row is the same in both matrices. Next, I create an empty list, which will be the row that we are going to append to the outcome matrix. I then loop over the column index and assign that to J during the loop. You can see that inside the loop, I'm adding the element in row index I and column index J of both matrices, and then simply append the output to the row that I have created before. This row then gets appended to the output matrix. Once I have looped over all the rows and all the columns, I return the outcome matrix. Scalar multiplication also works the same as in vectors. Just multiply each element with the scalar. So if you say, for example, R times the following matrix, 1, 2, 3, and 4, it's the same as saying 1R, 2R, 3R, 4R. Implementation in Python will entail another loop over all the rows and all the columns of a matrix. So let's say define scalar matrix, and it's going to take a matrix as input, which is lists of integers. The scalar is going to be an integer, and it's going to return the list of integers, so it's going to return a matrix. So first thing we do, for I in range 0 to whatever the number of rows is, and then for J in range O and whatever the number of columns is. I'm simply going to say, okay, going to take that element, so mi, and then we go into the column, and I'm just going to say, take the scalar and multiply that with exactly that element. And then in the end, I just return m. So let's create a matrix, two row vectors, 1 and 2, 3 and 4, and I'm going to say scalar matrix m is m, and the scalar is going to be 2. So it returns 2, 4, 6, and 8. So we only take one matrix as input and one scalar value as output. The type hints indicate that we are returning a matrix as output. First, I loop over the row indexes of the matrix, and then I loop over the column indexes for every row. Having the row and column indexes at hand, I can then effectively loop over every element in that matrix. All I then do is simply take the element, multiply it with the scalar value, and then replace that value in the same position with that new value. Okay, so the next one is going to be matrix multiplication. You remember from vectors that multiplying one vector with another is not just the product of matching elements in the two vectors. It is the same with matrices, because remember that vectors are just a special type of matrix. You can only do matrix multiplication with two matrices if the number of rows in one matches the number of the columns in the other. Hence, I of matrix A must be equal to J of matrix B. Else the dot product between the two is not defined. Since this video is not really about linear algebra, I suggest you consult a text or a video on matrix multiplication if you want details. In terms of notation, however, you can just add the two different matrices next to each other. This indicates that you are doing a dot product with them. So if you say A, so that's the first matrix, and then you can just add B to it. So that's the dot product. Here we have two matrices, A and B, for which we take the dot product. You can also be explicit and add the dot product notation between them. Though it's not the norm, you will most likely see them just next to each other. But you can also say something like this. So you can say A dot product B. There are also some special matrices that you will encounter. These matrices are usually represented with special variable. For example, there's a very important matrix called the identity matrix. It's a matrix where the elements along the diagonal are ones, and all the other elements in the matrix are 0. It is denoted with a bold uppercase I. Also, if you want to specify how many elements there are in the diagonal, you can add the number to the subscript. More often than not, though, it's just going to be I, and the number of elements is inferred from the context. So let's be explicit, though, and let's say that we have an identity matrix, and we say it has 3 elements in the diagonal. Then the matrix will look something like this. So 1, 1, 1, 0, 0, 0, 0, and 2 more O's here. So this is an identity matrix. We can create an identity matrix on demand in Python by just specifying how many elements we want in the diagonal. So we can say define get identity, and we're just going to give it one argument, which is n, which is going to be an integer, but it is going to return a matrix. So it's a list of integers, and the body looks like this. So let's initialize an empty matrix m, and then we're going to range over from 0 to whatever n is. And then what we do, so we say, well, create a row, which is a list of zeros, n times. And then in the ith element, put in the number 1. And then to that matrix m, we are going to append the row. And then in the end, we just return m. So let's do get identity. And let's set it to 3. So this is an identity matrix with 3 elements. We can also do 5. This is another matrix with 5 elements in it. As the sole input argument, we just take the number of diagonal elements as n. Everything else follows from that. However, you can see that we are returning a list of lists containing integers, hence a matrix. We start out by creating an empty list, which will represent our output matrix m. Then we loop over the range of numbers from 0 to whatever the number of diagonal elements should be. Here, it doesn't really matter that we're starting to count from 0. Inside the loop, I first create a row where I have a list of n zeros in it. This weird looking syntax basically repeats a list with a 0 in it n times and merges all the single lists into one. Hence, it will be a list with n zeros. Then I choose to replace the element at the ith element with 1. In the first iteration, it will be on column 1 in row 1. During the second iteration, it will be the second column in the second row. These rows I simply append to the output matrix. Like I said, the way the matrix looks is solely defined by the number of diagonal elements. Now remember inverse functions? Well, there's an equivalent matrix called the inverse matrix. A matrix A might, and I emphasize that it's a maybe, have a matrix B such that if you multiply A with B, the result will be an identity matrix. So this inverse matrix is denoted the same way as the inverse function. You take the name of the original matrix, A for example, and you put a little minus in the superscript like so. So if you have a matrix A, the inverse of this matrix A, so these are both letters. So the inverse of A, superscript -1. Actually, finding the matrix inverse is not super straightforward, but for some very simple matrices, there's actually a formula for it. If you take a simple 2x2 matrix, the inverse function is defined by swapping the diagonal elements and changing the sign of the off-diagonal elements. Then in the end, you need to divide every element by taking the product of the diagonal minus the product of the off-diagonal. We can implement this logic in Python. Note, however, that this is only valid for a 2x2 matrix. So let's do this. So we say define square inverse, and it takes M, which is a matrix. So it's a list of integers. And what it returns is another matrix. So it's list of integers. And the implementation looks like this. So if we say if the length of M, so the number of rows, is not equal to 2, then we are going to raise a value error saying not a square matrix. Also, if the number of columns in the first row is not equal to 2, or if the number of columns in the second row, if that one is not equal to 2, we are going to raise another error saying not a square matrix. Then we're going to set A to whatever is in the first row and first column. B will be whatever is in the first row and second column. Then C is going to be whatever is in the second row and first column. And then finally D is what is in the second row and second column. Then I'm going to calculate the determinant, which is, as I mentioned before, the product of the diagonal elements minus the product of the off-diagonal elements. And then in the end, what I'm going to say, well, the A of the inverse matrix is going to be D, because we need to switch them, divided by the determinant. B of the inverse matrix is basically just going to be the B from before minus 1, divided by the determinant. The C of the inverse matrix is going to be C times minus 1, divided by the determinant. And then finally, the D of the inverse matrix is just going to be original A divided by the determinant. Then let's create the inverse matrix, which is going to be, first row is inverse A, B inverse, and then the second row, C inverse, D inverse. Finally, let's return that matrix and create a matrix A, which is a square matrix, so 1 and 3 and 5 and 5. And the inverse of A is going to be square inverse, where M is equal to A. And we can have a look at this. So this is A. This is inverse matrix of A. And to actually run the matrix multiplication, I will import NumPy and convert the matrices to a NumPy array and then run the dot product between them. So I'm going to do this like so. So let's import NumPy. Let's say A is NumPy dot array A, and then A inverse is NumPy dot array A inverse. And then all we're going to do is A dot product, which you use the @ sign for, times the A inverse, and this returns this matrix. So the numbers on the diagonal are 1, while the numbers of the diagonal are reasonably close to 0. Hence, this is an identity matrix. It's not exactly close to 0 because of rounding issues. So what are we actually doing when defining how to calculate the inverse for a square 2 by 2 matrix? First, we are checking that there are just 2 rows. If not, we raise an arrow. Then we check for both rows that there are also just 2 columns in each row. Also, if that assumption is violated, we raise an arrow. Next, I simply extract the elements. I put the element in row 1 and column 1 into a row 1 and column 2. Next, I simply extract the elements. I put the element in row 1 and column 1 into A, row 1 and column 2 into B, row 2 and column 1 into C, and row 2 and column 2 into D. Next on, I calculate the determinant. Next on, I calculate the determinant, which is the number I get by taking the product of the diagonal and subtracting from it the product of the off-diagonals. Then I calculate the new elements in the inverse matrix. The new A will be D divided by the determinant. Remember that we switch the diagonal elements and divide each of them by the determinant. Then I take the off-diagonal elements each and multiply them by -1 and divide by the determinant. In the end, I switch the last diagonal element and divide by the determinant. To get an inverse matrix, I merely place the new elements in their corresponding places for the new matrix and return that new matrix. Now remember that I said a matrix might have an inverse. That is not a given. Not every matrix has an inverse. However, you can get a pseudo-inverse that gets you as close as possible to the identity matrix. Instead of the -1 in the superscript, you would use a plus or a dagger symbol in the superscript, like so. So let's say we calculate the pseudo-inverse of A. So we can notate this either with A and a plus at the superscript or an A with a little dagger in the superscript, which looks a bit like this. So there's no obvious implementation of the pseudo-inverse, so we're not going to do that here. When talking about the dot product, you might have asked yourself, well, how would I call the actual operations where we are multiplying each matching element with each other? Well, there's also an operation for that, which is called the Scheinerman product. It is indicated with a hollow point between two matrices or vectors. So remember, filled dot means dot product and hollow dot means Scheinerman product. So it looks a bit like this. So if you have two matrices and you want to get their element-wise products, so you have A, and then use a hollow dot, and then you have B. In Python, this is pretty easy to implement since we just need to get the product of the two matching entries. So we can say define header mart matrix 1 is list of lists of integers, and matrix 2 is a list of integers, and returns another lists of integers, and define like this. So we say if the number of columns does not match, well, we're going to raise an error stating that. So number of rows does not match. Then we're going to initialize a matrix, call this M3, and we're going to range over the number of row indexes. And we say, well, if the number of columns in row I is not the same for these two matrices, well, we have to raise another value error. So we say different. So we say number of columns does not match. Else we create a new row, initializing an empty list, and we're going to loop over the column indexes. So we say length of m, 1 ith row, and we're simply going to append to that new row the product of m1 at the ith row and the jth column, and m2 ith row, jth column. Once we're done with that, we're just going to append that row to M3, and then we're going to return M3 to the caller. And let's create two matrices, 1, 2, 3, 4. Next one is going to be 2 and 2, 3 and 3. And then let's create the header mart product of both of these matrices. Whoops, so it seems we have made an issue in the implementation. Yes, this is row new, of course. And again, I'm going to use the header mart on M1 and M2. And this returns the element-wise product. So the header mart function takes two matrices as input and produces a new matrix as output. So inside the function, the very first thing that we do is checking whether or not the number of rows in the first two matrices matches. If that is not the case, then we raise an error. Afterwards, we initialize an empty matrix by assigning an empty list to M3. Next on, we are going to populate that list. The first thing I do is I loop over the row indexes by ranging from 0 to the number of rows. The current row number gets assigned to the variable I. I then check that the number of columns in row I is the same for both matrices. If that assumption does not hold, we raise an exception. Otherwise, we initialize a new empty row by creating an empty list. I then range over the columns in row I and assign the current column index to j. Then, last but not least, I append the product of column j in row I on both matrices to this new list. Once I have looped over all the columns, I append the row to the matrix. Then in the end, we return the new matrix containing the element-wise product to the caller. The implementation is pretty straightforward, since we simply loop over all the elements in our matrices. Now, in some cases, you might need a matrix of ones, and this matrix is often denoted with this. You can also specify the exact number of rows and columns by putting it into the subscript. So you can also say something like this: m rows and columns. From the previous examples, it should be pretty easy for you to implement this yourself. You can just loop over the range of m at n and populate m rows with n number of ones in it. Another very important matrix that you will quite often see is the transpose. It's actually not a specific static matrix, but the transpose of another matrix. If you take the transpose of a matrix A, the columns becomes the rows and the rows become the columns. The transpose of a matrix is indicated with a capital T in its superscript. So let me give you an example. So if we have a matrix that looks something like this, so 5, 3, 2, and 3, 1, and 1. Now the transpose of that matrix, so superscript T, is going to look like this. So 5, and 3, 3 and 1, 2 and 1. You can see how we pivot the rows into the columns and the columns into the rows. Using Python, we can first populate a matrix with missing values in the form that we need it to be. Then we can just loop over the rows and columns and insert them into the switched position. I becomes j and j becomes I during the insertion. So we can say define the transpose of a matrix M, which is a lists of integers. And all it does is it returns another matrix, which is a lists of integers. And it works like this. So let's get the number of rows we have. So the length of M. Let's get the number of columns we have, which is the length. Let's just take the first row. And then we say, well, the transpose of M is going to repeat a list of nonce, the rows number of time for x in range O to cults, then for I in range O to number of rows, we are going to say for j in range O to the number of columns. And then what we're going to do in the transpose matrix, we're going to say, well, in the jth row and the ith column, put in the element from the ith row and the jth column. And then simply return that transpose matrix. So let's create a new matrix M. So it has 5, 3, and 2 in the first row, 3, 1, and 1 in the second row. And the transpose of that one is going to be this matrix, 5, 3, 3, 1, 2, 1. Okay, so I first get the number of rows and columns. Note that I take a little shortcut here and don't check if the number of columns is really equal in all rows. So then I create an empty matrix with a bunch of missing values. However, the important thing is that m_t is the shape that I need it to be. The list comprehension that I built might be a bit complicated to read, so let me explain that to you. Obviously, since it is a list comprehension, the result will also be a list. You can see that I range over the number of columns, which will be the number of rows in the transpose for every column index I. I create a list that has the non-value, the number of times that is equal to the number of rows we have in the original matrix. Then I loop over the row and column indexes. This, in essence, boils down to iterating over every single element index that we have. What I then do is replace the values in the empty matrix. Notice that the row index of the transposed matrix is the column index of the original matrix, and the column index is the row index of the original matrix. All I then do is put the respective values in and return the final result to the caller. You can see that my input matrix has 2 rows and 3 columns. The transpose of that matrix has 3 rows and 2 columns. For some algorithms, the trace of a matrix becomes important. The trace of a matrix is simply the sum of its diagonal elements. You indicate the trace of a matrix A with a TR in front of it. So you can say the trace of matrix A. And that is nothing else than the sum of its diagonal elements. So we start at I equal to 1, and we go whatever is less, the number of rows or the number of columns. And then we take every element of A at row I and column I. So the sum operation might need a little explanation. As you can see, we are going from I equals 1 to whatever is less, the number of rows or the number of columns. While it's the same for a square matrix, you need to account for oddly shaped matrices that are rectangular. Assuming that we have a square matrix where the number of rows is equal to the number of columns, we then just take the element at row I and column I. This is equal to the diagonal element in row I. In the end, we just sum all of these. So let's do this in Python. However, for demonstration purposes, we will also loop over a rectangular matrix. So define the trace, and as input it takes M, which is list integers, so it's a matrix. And it returns list integers, so it's another matrix. And we implement it like this. So say index end is equal to whatever is less. So I'm giving it a list here. either the length of m, which is the number of rows, or the number of columns, where I just check the length of the first row. I just need to make sure that I'm closing that list at the right position. Yes, this should be fine. And then initialize the trace to 0. And then for I in range, we start at 0, and then whatever the index end is, so either the number of rows or the number of columns. And then we say, well, add to the trace the following value, go into m, go into the ith row and the ith column, and then return the trace. So let's create two matrices. So 1 and 2, 3 and 4, 5 and 6. So this one has more rows than columns, and M2 has more columns than rows. So 1, 2, and 3, 4, 5, and 6. And then what we're going to do is get the trace for M1. So we sum the diagonal elements, which is 5. So we add 1 plus 4, which is 5. And then we get the trace for M2, which is 6, because we add 1 and 5, which is 6. So just as the formula prescribes, we are terminating a loop at whatever is the minimum, the number of rows or the number of columns in our matrix. The first line of code just checks what that number is. Then I initialize the trace to the number 0. I then start my loop to range from 0 to whatever the end index is that we have found using the minimum operation. To the trace, I then add whatever the value is at row I and column I. The result will be returned to the user. I apply this function to two matrices. The first matrix has more rows than columns. Hence, we should stop the iteration at I equals 2, since we only have 2 columns. In the first iteration, the diagonal is 1, so we add that to the trace. In the second iteration, the diagonal element is 4. Again, we add that to the trace, which is now 5. Notice that we have already reached the last column of our matrix, so there's no further diagonal element. Yes, we have another row at the bottom, but we have nowhere to go into the right. Hence, we terminate the loop. The second matrix has more columns than rows. Again, the iteration will stop after 2 iterations. The first diagonal element is 1. The second is 5. Hence, the trace sums to 6. Yes, we have more columns to the right, but we cannot move further downwards. A very important aspect of every matrix is its rank. The rank actually tells you a lot about the properties of a matrix. I won't go into the details of the rank and the underlying concepts, since you can fill entire lectures on that one. But basically it tells you whether one column or one row is simply made up of other columns or rows. Hence, it will tell you if the rows and columns of a matrix are independent of each other. A square matrix with 2 rows and 2 columns that has independent rows and columns is said to be full rank. Its corresponding rank is 2. The rank of a matrix is written down like so, and it's a simple number. So you can say, for example, rank of matrix X. There's also a corresponding null space, which is the set of vectors that if you multiply the matrix with this vector, you will get a matrix full of zeros. And it's denoted like so. So you can say the null space of a matrix, let's call this one actually Z. That one is equal to the set of vectors where the vector X, if you run Z times that vector X, you will get a matrix full of zeros. There's no straightforward way of implementing the rank calculation and null space calculation in Python. Hence, I will not show you the implementation of that. So we've encountered that problem more than once, that some of the calculations are rather involved. If you're curious about how to do that in Python, check out the linalg module in the NumPy package. With these words, we are going to leave the world of linear algebra and we are going to enter the world of calculus. Just as linear algebra, the topic of calculus is a big one. And just as linear algebra, calculus brings its own set of notation, which we will have a look at now. So let's start with the notation for limits, as they are pretty important. Let's say you have a function f of x, and you want to know what the output value will be the closer you set x to a specific value a. You would write it like this. So you would say the limit as x approaches a for f of x. On the right, you can see our good old friend f of x, which is just a function mapping a number x to some output number. However, on the left, we put the lim keyword, and below it, we put x towards a. So what this whole expression is equal to is the number that you will get closer and closer to the more you change x towards a. What this means will probably be a bit clearer when we create an implementation for it in Python. Remember, we want to get the number that we get closer to as we move x towards that value a. So we can say define limit, and it takes an input f, which is a callable, a, which is a float, and returns a float. Then we create some approximation multipliers. It's a list with 0.1, 0.5, 0.9, 0.99, 0.999, and 0.9999. Then the output values are take f of a times x for x in those approx mult list. Then for approximation and output value, so for every approximation output value in zipping these two lists together, prox mult and output vals, we just print a string saying the approximation multiplier, which is approx, and the value we want to get out. And then in the end, we return the actual value, which we're going to round. So we take the output vals and we just take the last element there. And let's actually round this to the 6th decimal. And I noticed that I forgot to close the list comprehension here. So let's run this. So function is defined. And let's actually run this and say we define this for f being a lambda function. Take a as input and we just raise it to the 2nd power. And let's set a to 2. And there you go. Okay, so this implementation is nothing you would use in a production-like setting, as there are other methods that get you a more precise number. However, it is very helpful to get the point across. So what we do in the function parameters is that I accept a function f. Its type being a callable means that it's a function that we can actually call. We then also take another argument a, which is a number. What we will later do is use a as an argument to f. Note that this also returns a number. Then the first thing I do is create a list of approximation multipliers. I will later multiply our input value a with these values to get a general idea of to what this value approximates to as we get closer and closer to this value a. The first decimal stands for 10% of a, then half of a, then 99% of a, and you get the general idea. Next on, I'll calculate the corresponding output values by running a list comprehension. For every element in the list containing the approximation multipliers, I take a, multiply it with that approximation multiplier, and run that through f. The result will be a list of values that gets closer and closer to what f of a actually is. I then loop over the matching values of approximation multipliers and output values and print them in a table. This way you can see what the output value converges to. Finally, I then round the last item of the output values to the 6th decimal place and return that value. Running this on the function that takes a to the 2nd power with 2 as its input, you can see that the output value gets closer and closer to 4 as the input gets closer and closer to 2. This is the whole point of a limit function. The notation looks a bit scary, but this is basically all it is doing. Actually, the implementation I've just shown you is a special case of the limit. Notice how we start with a small value, 1/10 of a, and then get closer and closer to a. Here we are approaching a from the left side of the number line. However, we could have also started by using large multiples of a and get closer and closer to the actual smaller value. In this case, we would approach the limit from the right side of the number line. In this case, both limits are the same and it doesn't really matter from where we come. However, if you want to emphasize that the limit you're looking at is coming from the left, you can add a minus to the superscript like so. So you can add a minus just here. I think this notation makes sense since you start with something less than a, hence a minus sign. Should you want to show the limit coming from the right side, you can use the plus sign on the superscript like so. If you want, you can create your own implementation of the right side limit. all you need to do is switch out the approximation multipliers. Probably the most common limit you will see is the limit to infinity. So to what value does the output value of a function converge to as the inputs get closer and closer to infinity? Positive or negative? For that, you can just replace the a in the limit with the infinity sign like so. So you can say something like lim as x gets closer to infinity for f of x. Or you could say the limit as x gets closer to minus infinity for f of x. Just as important as limits in calculus are derivatives. What the derivative shows is the rate of change for a function at a specific point. So imagine that you have a nonlinear function like the square, for example. So we're talking about something like f of x equals to x squared. If we draw that function, we will see that the rate of change is not the same. The further we move down the x-axis, the bigger the increase in the y value. So the graph would look something like this. What we could do is, for every point on the graph, we can take another point that is infinitely close to that point and calculate how much y changes when moving x. Luckily, we don't have to do that for every point in the function. As there is a function, we can just plug x in and it will tell us the slope of the function at that exact position. And that's the derivative. So let's assume that we have this simple function, so x squared, which just takes one input x and it squares it. And it returns that as a y. So let's assume we have this simple function which just takes one input x, squares it, and returns it as y. There are actually two ways you can write the derivative of that function. The first one I'll cover is one that actually explains very well what we are actually doing. And it looks like this. So you can say delta, so this triangle here, y over delta x. And it's the same as saying delta f over delta x, which is the same as saying dy over dx, which is the same as df over dx. All of these notation actually mean the same thing, and you might see either of them. Let me start with the first one. The first character is not a triangle, but the Greek letter delta. Delta usually stands for change. So the way we can read the first equation is a tiny change in y over a tiny change in x. And that perfectly describes the derivative. How does y change in relation to changes in x? In the second equation, we simply replace the y with a function name f. Y represents the outcome value and f stands for the function. However, they both stand for the same thing, the output value. Then follows the same as before, but we replace the delta letter with the Latin letter d. I actually prefer the first version since delta often stands for change, and relating the output value to the input value makes more sense in my view, but you might use or see either of them. This notation is called the Leibniz notation. However, there's also a second way to write down the derivative, which is called Newton's notation. If you want to get the derivative of a function f, you can denote it with a small prime mark on the top. So you can say f prime x. For our implementation of the derivative, we need to remember that the derivative basically tells us by how much y changes if we change x by a tiny amount. While there is a very precise way of calculating this, I'm going to use a more naive approach that just changes x by a tiny bit and sees how much y changes. So we're going to define a function called derivative. And it takes an input f, which is a callable, and an input x, which is a float, and it returns a float. So let's calculate y by just using f of x. So we use the function f and put x in as an input. Then we calculate a change, by how much we're going to change x. So we take x, and we're going to calculate the 1,000,000, so a tiny fraction of it. This is the amount of change we use. Then let's calculate the new y, where we say, okay, f of x plus that tiny change. Then we calculate the slope. So we say take y delta, subtract from it y, and divide it by the amount of change, and then just return the slope. Okay, first we define functions. So square is lambda x, where we square x. Then let's calculate the derivative. So f is going to be a square function and x is going to be 2, which is about 4. And let's do the same for the point x equals 4, which is about 8. Our derivative function is taking two inputs, a function called f and a value called x. It returns a single number in response. The very first thing we do is calculate y by just running our value x through the function f. In order to calculate the change in y for a tiny change in x, I then calculate that tiny change in x by multiplying it with 0.0001, which equates to 0.01% change. Hopefully this will be small enough. Then we get the actual change in y by running x plus that tiny change through f and getting the output value. Then we get the new y by running x plus that tiny change through f and getting the output value. Afterwards comes what is called the difference quotient. I divide the change in y by the change in x. If you now remember that Leibniz notation, this is actually exactly what the notation says. The change in y divided by the change in x. To show the function in action, I first create a lambda function that just squares x, and I save that to f. We then get the rate of change for that function at x equals 2 and x equals 4. The resulting values are 4 and 8 respectively, with some rounding issues. Remember that I told you that there is a function to calculate the derivative with complete exactness. Basically what you do is you take all the x's with an exponent, decrement the power by 1, and multiply that x by that number. All constants get dropped. So x to the power of 2 becomes 2x, and 2 times 2 is 4, and 2 times 4 is 8. Hence the derivatives that we calculated before, check out. But what if we want to get the change of the change? Well, then you're looking at the derivative of the derivative. In Leibniz notation, you would just add the degree of the derivative to the superscript of the delta or d in the change for y and the superscript of x. So it would become something like this. So you have delta, and you're going to get the second derivative of y over change x. I will put a 2 here. Newton's notation is pretty easy in that regard, as you can just add the corresponding number of prime arcs. So you can just say f prime prime x. In that case, I think Newton's notation is actually better. If you want to be specific and say that the value of a derivative at a specific value, such as x being equal to a, you can have a bar on the right and put x equals to a into the subscript like so. So you can say f prime of x, where we set x to a, which is the same as saying delta y over delta x, where we say x equals to a. Okay, so notice how we relate y only to one other variable x. In many functions, you have more than just one variable. In that case, you want to have the partial derivative since you keep all other variables constant. For the partial derivative, we have the special version of d. So it looks something like this. F over xj. Here we take the partial derivative of our function f with respect to the jth input variable. Obviously, you will have as many partial derivatives as you have variables. The way of how to actually calculate the partial derivative is the same as the logic that it implies. Remember, the partial derivative gives you the rate of change for the output of a function when the jth variable changes by an invisible increment while keeping all other variables constant. Hence, when you calculate the partial derivative, you do the same thing. Just keep all the other variables constant. So with that in mind, let's attend to our implementation in Python. First, let's define our partial derivative function. So as input, it takes f, which is a callable, Then it takes some keyword arguments, which is just a dictionary. Keys are strings and the values are floats. And we take the name of the variable for which we want to calculate the partial derivative. First thing we do is we run our arguments through f, save the output to output. And then what we're going to make is we're going to change our arguments by just copying the original input first. So this dictionary with the arguments, save that to keyword arguments change, and then we calculate a tiny amount of change by just taking the variable in there and getting a tiny change in there. And then we're going to overwrite the variable in this new dictionary. So we're going to increment that value by a tiny amount. And then we calculate the new output, just unpacking the keyword arguments into the function. Let's calculate the slope, which is just going to be the new output minus the old output divided by the amount of change. And we are returning that slope. Okay, next one. We need to define a function that we actually want to calculate the partial derivative on. So it takes two arguments, x and y, and it returns an integer. And all it does is it simply returns x to the power of 2 plus 2 times y plus 6 times y times x. And this is all the function is doing. And then we define the arguments, which are, so x is going to be 4 and y is going to be 2. And then we calculate the partial derivative for this function f multi. And the keyword arguments, we are just going to set equal to these arguments. And first off, we are going to calculate the partial derivative for f multi with respect to x, which is 20. And then we're going to do the same thing for y, which is 26. All right, so there's a lot of things happening that we are already familiar with, but there are also some different things. So let's check what is happening here. So first notice the function signature. So we take a function in as input. That hasn't changed. This is obvious since we want to get a partial derivative of a function. Then we have a quarks argument. That is a dictionary that takes strings as keys and floats as values. Okay, so this dictionary will hold all the values for our variables. Then the last argument is the name of the variable for which we want to calculate the partial derivative. As with the previous implementation, we first calculate the regular output using the arguments as they come in. Then I also calculate the amount of change. In order to do that, I first copy the input dictionary of variables into a new dictionary. Then I extract the value for the target variable and calculate a small change again by multiplying it with a tiny amount. In this new copied version of our arguments, I increment the target variable by that amount. Hence, we now have two dictionaries. Quarks holds the variables with the values as they come in, while quarks change is the same dictionary with the target variable incremented by a tiny amount. The rest in that dictionary is still the same. We then calculate the output of the function again, but this time we use the dictionary that contains the arguments with the target variable changed by that tiny amount. Hence, just as we described it with words, we change our target variable by a tiny amount and keep all the other variables constant. Then, the same as before. I simply calculate the slope and return that value to the caller. Obviously, I need to have a function that takes more than one argument, so I define f multi, which takes x and y as input. It first squares x, multiplies y by 2, and takes 6 times the product of x and y. All of this is then summed. Hence, we have two variables as input. For the arguments, I set x to 4 and y to 2. I then calculate the partial derivative for f with respect to x and y each. We can validate this by first calculating the derivative by hand and then comparing that to the actual values we got. So for x squared, the derivative with respect to x is 2 times x. We can ignore 2 times y since this is just a constant. 6 times y times x becomes 6y since x to the power of 1, which it currently is, simply boils down to 1 times 6 times y. Put that all together and you get 2 times x plus x times y. Remember that x is 4 and y is 2 in the input. So the rate of change for x at x being 4 and y being 2 is 2 times 4 plus 6 times 2. This is 20. And comparing that to the output of our partial derivative, it's the same except for some rounding issues. I leave the partial derivative of f with respect to y to you. As you can see, something as seemingly complicated as the second derivative boils down to some very simple logic in Python. Talking about notation, you can also use the denotation, by which you say you take the derivative of f with respect to x, like so. So you can say dx for this function f, and this is the same as saying partial derivative f, partial derivative x. If you work in machine learning, you might have heard the term gradient. The gradient is very important if you want to train a model, and based on the training data you see, you want to change the values of your function. Basically, what the gradient is, it is a vector of all the partial derivatives. So for example, if you have variables x1 all through xn, you can just pack all of them in a vector like so. And I'm going to create a row vector here because I'm running a bit out of space. So you can say partial derivative f, partial derivative x1, then you have partial derivative f, partial derivative x2, all the way to partial derivative f, partial derivative xn. And this vector is also denoted with grad f, so you can say grad f, gradient, or you can also use a rotated delta f. The other big thing in calculus, except for limits and derivatives, are integrals. Integrals are pretty much the opposite of the derivative. While the derivative is used to show the rate of change at a specific point, the integral sums the changes over a specific interval. This interval is also mentioned in a notation which looks like this. So integral a b for f of x dx. The S-shaped character indicates that we are running integration from a to b. Then we mentioned that we would like to calculate this on the function f of x. Lastly, we define the variable that we would like to integrate the function with respect to. In this case, it is x, as it also just takes x as an input. Another interpretation of the integral is that it calculates the area under the curve. So if f of x is a function and we want to know how big the area under the curve is between point a and b, we can calculate the integral. Just as with derivatives, there is a formula to get the integral which will yield exact results. However, for our simplistic implementation, we will use another approximation. One easy way to approximate the area under the curve is to slice the range from a to b into many small steps, and then for each step we approximate the area under the curve by running a rectangle from y equals 0 to whatever y is at the midpoint on x. We can then very easily calculate the area of that rectangle. So let's implement that in Python. Again, we are going to do that for a simple function that just takes one input x. So let's define our integral here. So f is going to be a callable, start is going to be an integer, and it's going to be an integer, and we are going to return a float. So actually, if the end is less than start, let's switch this around. So start will become end, and end will become start. And then let's set the number of steps to 10,000. Let's calculate the amount of delta we want to run. So end minus start divided by n. So how much we're going to switch x for every step. Then let's start the integral sum with 0. And then for every step in these 10,000 steps, what we are going to do is we're going to calculate our new x, which is just the starting value, plus I times the amount of delta that we need to go. And then we going to increment the integral sum by running f of x times that delta amount. And then we just return the integral sum. There you go. And let's create our square function. So this is going to be lambda x. So x to the second power. And then we calculate the integral for f being the square function, going to start at 3 and ending at 10, which is 324. As usual, let's look at the function signature first. We give it a function as input and a start and an end for the integral. That's it. Then inside the function, we swap the start and end if the end is actually less than the start. n resembles the number of rectangles we are going to draw for approximating the integral. The bigger the number, the better your approximation will be. Closely related to that is the size of the rectangles, which are saved under the delta variable. This represents how much on the x-axis we move for every step. I also initiate the sum of the integrals to 0 since we will add to that the value during every step. Next on, I take n steps. During every step, I get the x that I want to put into the function by taking the start value and add to it the amount of delta I need to add. This is done by taking the product of the delta and the step we are actually on. Then comes the most important point where I just calculate the size of the rectangle by taking the height, which is the result of running x through f of x, and then multiplying that with the width, which is the delta. That value gets added to the integral sum. In the end, we just return the integral sum value. The function that I want to integrate over will simply be the square of x again. I use this function as input to f and calculate the integral going from 3 to 10. Again, we compare that to the actual formula to calculate the exact integral. For x squared, that would be x cubed divided by 3. If we run that through, we get pretty much the same value. So if we would run 10 cubed divided by 3, so this is our end, and then from it we subtract the start, which is going to be 3 cubed divided by 3. So if we run this, we get 324, which is the same as before. So again, the way you can interpret the value you get from the integral is the area under the curve for x squared from x3 to x10. With that being said, we are closing the chapter on calculus and move to our last topic, which is probability and statistics. Like the other sections, statistics and probability comes with its own special set of notation. However, it doesn't have as many weird operators as the others. So let's start with the most basic concept, probabilities. You probably have a rough idea of what probability is. Let's say there is a set of possible events. What you're usually interested in is the probability of one of these events actually happening. The set that contains all the possible events is usually denoted by the Greek letter omega, like so. Let's say we have an event A, which is a member of this set of possible events. The probability of that one event happening is usually denoted as P of A, where P stands for probability. So it's going to be the probability of A. You can also say what the probability of an event not happening is by adding a little prime to the event. So the probability of A not happening is P of A prime. Maybe just one event happening is not that interesting. You can chain multiple events together by using the AND or conditional probability. If you want to calculate the probability of event A and B happening, you just join them together with either an upside down U or a caret symbol like this. So we can say probability of A and B, and that's the same as saying probability of A caret symbol B. The OR operator is the same for both, just rotated by 180 degrees. So we can say P of A or B, and that's the same as saying P of A upside down caret symbol B. And the last one is conditional probability. If you want to say something like the probability of A happening based on a condition that B has already happened, you just put a bar after the thing for which you want to get the probability. So you can say the probability of A conditional B. And the way this reads is like the probability of A given B. You can of course mix and match. Your expressions can be as complicated as you want them to be. So an important concept in statistics is the random variable. This could be almost anything. For example, it could be the temperature in your hometown tomorrow at noon. These are usually denoted with a capital Latin letter, while the actual values are in lowercase letters. So for example, the temperature might be denoted with x, while the actual measured temperature at a certain point might be lowercase x. So you can have x, this is our random variable, and the actual value we measure is x. And we generally have an idea of what we would expect the value to be. This is called the expected value and is often the same as the mean. You would write the expected value for x like so. So we would say E of x. Often we use the Greek letter mu to stand for the actual mean value. It's used interchangeably for the expected value. And you can be very precise and add the actual variable name into the subscript. So we can say mu for x. The expected value can also be more precise if it's conditioned on something else. So for example, if someone asks you what the temperature of your hometown usually is, you might just give the person the average value. Maybe that is 20 degrees Celsius over the year. However, what if that person asks you what the temperature usually is in winter? Hence, they're asking for E of x given W, where W stands for being winter. So we would say something like E of x given W. And the mean is calculated very easily by just taking all the values, summing this, and then dividing by the number of elements. So let's do that in Python, where we take a list of values as input for which we want to calculate the mean. So we can say define the mean. So we get a list of input values and then return a single value. And I do this in one go. So return the sum of vals divided by the length of vals. And let's calculate the mean for the following data 5, 10, and 25, which is 13.33. So that was so easy that we could do this in a one-liner. You simply get the sum of all the values and divide by the number of elements in that list. That's it. Obviously, if you want to use conditional probability, you could just keep the values for which this condition is true. So when looking at the values we put in, we can say that we would expect a value of 13.33. The mean value also has some other notation. And you might also see the variable with a bar on top. So it could be something like uppercase x bar, or it might even be lowercase x bar. And if you want to put the operation we just did into mathematical notation, you can also write the operation like so. So we can say x bar is equal to 1 over n times the sum. So we're going to use the sum operator, where we start at 1 and assign that to k all the way to n. And we take that variable x and we take the kth observation. So remember from the sum operator that what we do is we loop from 1 to n, where n is the number of observations for that random variable x. During every step of the iteration, we assign that loop index to the variable k. We just sum all the values inside the vector for our random variable. However, we also multiply that by 1 over n, which boils down to dividing the sum by the number of elements, just what we did in our implementation in Python. An alternative measure is also the median. What the median does is simply ordering your data from lowest to highest and taking the value right in the middle. This value is denoted with a little tilde on top of the variable name, like so. So you can say x, and then at top we put a little tilde. To implement the median, we can simply order our array of values and take the value in the middle. If we have an even number of elements, we just take the average of the two values in the middle. So we can say define the median, where as input we take a list of floats and we return a single number. And what we do is, so first of all, sort our data. So use the sorted function on vals and save that to data sorted. Then calculate the number of elements that we have. So the length on data sorted. Now, if the length or the remainder of the division by 2 is equal to 1, then what we do is the median is going to be, well, data sorted, and we take the element at length divided by 2. Else, what we do is we take the first midpoint, which is just data sorted, and then we take the length divided by 2 minus 1. Then we take the second midpoint, we say data sorted length divided by 2. And then all I need to do is I need to calculate the median by calculating the average of these two midpoints. So I say mid1 plus mid2 divided by 2. And then in the end, I return the median. Now let's do this for a few values here. So the first one is going to be pretty easy. So let's do 50, 1, and 100. And let's do the same for an even number of elements. So it's going to be 50, 70, 101. And this is 60. So we get the input data in vals. First thing we do is, with that, we sort the list. By default, it will sort the data from lowest to highest. Then I also check how many elements are inside that list. This will become important since I need to find out what index is right in the middle of that list. So the first thing I check is the modulo of the number of elements divided by 2. The modulo tells you how much is left after division. So if you divide 4 by 2, nothing is left. Hence the modulo is 0. But if you divide 5 by 2, 1 is left, since you can divide 4 by 2, but not 5. This modulo is the remainder after running the division. If the modulo of dividing the number of elements by 2 is 1, that means we have an odd number of elements. Having an odd number of elements is the easiest case, since we can just take the element right in the middle of that list. Hence, we extract the element at the position of dividing the number of elements by 2. The 2 division characters here do integer division. That means we round the result to the floor. It doesn't really make a difference here, but with rounding errors ever present, it makes sense to have the built-in guarantee that we have a whole number. The only other possibility left is that the modulo is 0, or in other words, we have an even number of elements. In that case, we just take the mean of the 2 elements in the middle. For that, I calculate the index of the 2 numbers and then calculate the mean of the respective values. Then I run 2 operations, and the first operation is easy. The number of elements is odd, and it's obvious that the number right in the middle is the value 50. The second one is a bit trickier, since we have an even number of elements, and the 2 values that are in the middle are 50 and 70, for which we need to take the mean, which is 60. Another important measure is variance. Variance is measuring how different the data points are. So for example, let's say that you get some daily stock prices and you want to calculate how volatile a stock is that you invest in. Let's call the random variable P for price. And you would denote the variance like so. So we would say the variance for our variable P. And we could also write it like this. Sigma squared for the variable P. Now these 2 notations are equivalent. I think the first one is pretty self-explanatory. The second one needs some explanation. So we first use the Greek letter sigma, which we square. Also, in the subscript, we see the name of the random variable. Now, why do we square sigma? Well, that will become obvious once I tell you how we actually calculate the variance. What we do is, we take every value and subtract from it the mean value. And that we take and square. Then, for all these values that we have, we calculate the mean. So hence what we are really doing is taking the expected squared deviation from the mean. So sigma squared P is nothing else than the expected value of, and I need to put some parentheses in here, P minus its expected value squared. We can of course implement that very easily in Python. We are actually going to reuse our mean function from before. So we can say the variance, so we get the variance for a list of numbers and return a single number. So what we do is, first thing, we need to calculate the mean of our values. Then we need to calculate the squared deviations. And we need to do that for every single element. So we take x, from it we subtract the mean value, and then we square that. And we do that for every x that we get in our vals list. Then what I do is I calculate the variance by simply saying, well, that is the mean of those squared deviations. And that value I will return, and that is my variance. Now let's calculate this for some numbers. So let's say variance for vals equals 100, 120, 110, 130, and 90. And that is 200. So again, we take a whole bunch of observations for our variable as a list of floats. We will return a single value that describes the variance of this list of values. The first thing we do is calculate the mean of our values. Next, we calculate the squared deviations from that mean. This is produced from the list of original values by simply subtracting the mean and squaring all of that for every single value. From that list, we get the mean, which represents our variance. So we can say that the squared average deviation from the mean is 200. However, this might not be super easy to understand, so what people often use is the standard deviation, which is simply the square root of the variance. Hence, this will represent the average deviation. Since we just take the square root of the variance, you will not be surprised that the notation for the standard deviation is just sigma. So our standard deviation is denoted as sigma, and this is nothing else than taking the square root of sigma squared. We can extend the variance function for our implementation of the standard deviation. So we can say standard deviation for a list of values, which returns a single number. And this is going to be variance. Well, so what we do is we just calculate the variance. Then we calculate the standard deviation by taking the variance and just raising it to the half power, which is exactly the same as taking the square root. And then we just return that value. And let's calculate the standard deviation for the values 100, 120, 110, 130, and 90, which is 14.14. So we use these same values as before, which represent our daily stock prices. So what this tells us is that we can expect a deviation of $14 per day. Another equally important measure is covariance. It measures the relationship between two random variables. So for example, if you have a random variable x that represents the temperature at a given day and a random variable y that represents the amount of ice cream sold on that day, the covariance would show that these two values move together. And you would write it like this. So you'd say the covariance of x and y. You can even extend this to many more variables. So let's say you have a vector of random variables, which we call x. This might be represented with a bold capital X. So you could say, well, X is a vector of a whole bunch of random variables. So we can say X1, X2, all the way to Xn. And we can create a matrix that has all the covariances between the different random variables in that vector. And we would often represent that matrix with the capital sigma. So we would say sigma. To calculate the covariance between two random variables, we just take the product of the respective deviations from the mean, sum all of these values, and divide by the number of elements. This will become clearer when we implement it in Python. So let's say define covariance x, which is a list of floats, and y, which is a list of floats. And we want to return a single number, which is the covariance. So first thing we do is we calculate the mean for x, then we calculate the mean for y. Then I'm going to initialize a variable called covariance sum, which I set to 0. And I'm going to loop over those values. So for val x and val y in zipping these two together. So we're going to loop over in pairs. And we're going to say, take the covariance sum and increment that one by taking the x value and subtracting from it the mean of the x, and then take the product of taking the y value and subtracting the mean of the y value from that. And this is how we increment the covariance sum in every step. And then I take this covariance sum and divide by the number of elements that we have. And this will give me the covariance. So let's create two variables. So x is going to be 10, 40, 50, 60, and 90. And then we have y, which is going to be 11, 32, 43, 55, and 75. And then we're going to calculate the covariance. X is x and y is y. And that is a covariance of 558. So we take two vectors that represent our random variables x and y, and we return a single value. The first thing we do is calculate the mean for each vector and save it to a respective variable. Then we initialize a covariance sum variable to 0 and iterate over matching elements in the two vectors. For every iteration, we simply take the product of the deviations from the mean of the two and increment the covariance sum by that value. Finally, we return the covariance sum divided by the number of elements in the vectors. The bigger the resulting number, the stronger the connection between the two variables. Now, it's probably obvious from looking at the implementation that the number is potentially unbounded and scaled by the numbers you have in the two vectors. However, you can also get a number bound between -1 and 1 by taking the covariance and dividing it by the product of the standard deviations of the two variables. This number is the correlation coefficient, and you can write it like this. So we would say the correlation between x and y is basically just taking the covariance of the two, x and y, and you would divide that by taking the standard deviation of x times the standard deviation of y. And we can reuse our covariance function for implementation of the correlation function. So we can say define correlation. So x again is going to be a list of floats, y is going to be a list of floats, and we are returning a single number. And what we're going to do is first calculate the covariance by using our trusted covariance function, where x is x and y is y. Then we just need the standard deviation of x. So for that we can use our old standard deviation function, do the same for y. And then we just need to calculate the correlation, which is just taking the covariance and dividing by the product of the two standard deviations. Which will give us the correlation coefficient, which we just return to the user. Let's create two data series, so 10, 20, 30, 40 for x, and for y we take 12, 32, 41, and 55. And then let's calculate the correlation for x being x and y being y, which is 0.99. The closer the absolute value of the correlation coefficient is to 1, the closer the relationship between the two variables. The sign in front tells you the direction of the relationship. If it is positive, the numbers move in sync. If one goes up, the other goes up, and vice versa. A negative sign turns that around. If one goes up, the other goes down, and vice versa. So looking at the number we got, we can say that there's almost a perfect relationship between the two variables. Just looking at the data tells you that the two move very much in sync. When you look at your data, a good way to scale your data is the z-score. What the z-score does is, for every observation, it says how many standard deviations away from the mean that value is. And you can indicate it using a z with an I in the subscript for the single observation in the variable. So we can say the z-score for the ith observation is just taking the ith observation, subtracting from it the average value, and divide that by the standard deviation. Now, as before, mu stands for the mean of the variable and sigma stands for the standard deviation of the variable. X subscript I just stands for the ith observation, or the ith value for that random variable x. For the implementation in Python, we are going to reuse much of the stuff that we've built before, since we do need to know the mean and the standard deviation of our variable. So we're going to say define z-score for some values, which is a list of floats, and we're going to actually return another list of floats. So it's just the same data scaled. And what we do is we first need to calculate the mean. So let's use the mean function for that one. Then what we need to do is we need to get the standard deviation. So for that we can use the standard deviation function. And then what we need is a list where we can put the z values in. So this is going to be an empty list for now. And then I'm going to loop over the values in vals. And what I do is I first calculate the single z-score by taking the value and subtracting from it the mean value and divide by the standard deviation. Then I take vals z, so this list, and append to that one that z value that I have. And then in the end, I just return that list to the caller. So let's create some z-scores. So z-score for vals and do 1, 5, 50, 80, 100, and 120. So we get back minus 1.29, minus 1.20, minus 0.2, 0.45, 0.9, and 1.34. Again, we just take a series of numbers as input. Then we calculate the mean and standard deviation for that data series. I then initialize an empty list that will hold the z-scores for our original data. Looping over every element in our original data list, I first calculate the z-score for that single value by subtracting the mean value from the original value and then divide that result by the standard deviation. In the end, I merely append that to the list of z values that I have initialized earlier and return that value to the user. And with that, we have reached the end of this video. I hope it has helped you understand some of the most important notation. Also, I hope that you were able to see that behind some of the very daunting looking formulas and operators, there's some really simple logic behind them.